13.8 billion years ago, everything we know exploded into existence from a point smaller than an atom. But the James Webb Space Telescope just found galaxies that were already ancient when the universe was supposedly still a baby. We're seeing stars that formed heavy elements before the cosmos had time to cook them. Massive black holes that grew impossibly fast, and structures so perfectly organized they shouldn't exist in a chaotic young universe. The most powerful telescope ever built wasn't meant to destroy our origin story, but that's exactly what it's doing. Prepare yourselves. We begin. The James Webb Space Telescope cost $10 billion and took 30 years to build. But this wasn't just about getting better space photos. Scientists had a specific mission: prove that our story of cosmic creation was absolutely correct. For decades, we've told ourselves a simple tale. The Big Bang happened 13.8 billion years ago. Then came 400 million years of cosmic darkness while the first stars slowly formed. Those early stars were supposed to be simple, made only of hydrogen and helium. Galaxies should have grown gradually, messily, over billions of years through countless collisions and mergers. This timeline wasn't just theory. It was the foundation of modern cosmology. Every textbook, every documentary, every explanation of how we got here relied on this sequence of events. The James Webb Telescope was designed to be the ultimate witness. Its infrared vision could peer back to the cosmic dawn and show us those first, primitive stars struggling to ignite in the darkness. We expected to see a chaotic, violent universe slowly organizing itself into the cosmos we know today. The telescope's mirrors were polished to perfection. Its instruments calibrated to detect the faintest whispers of ancient light. Scientists prepared to celebrate as observations confirmed what computer simulations had predicted for decades. The early universe should look young, disorganized, and exactly as messy as you'd expect from a cosmos just learning how to exist. But when James Webb opened its golden eye and looked back toward the beginning of time, it didn't find confirmation. Instead, it discovered something that made astronomers question everything they thought they knew about cosmic history. The telescope that was meant to prove our origin story might instead destroy it completely. What we found challenges not just the details of how galaxies formed, but the entire timeline of cosmic evolution. The implications reach far beyond astronomy. If our most fundamental story about reality is wrong, what does that mean for physics, philosophy, and our place in the universe? The discoveries waiting in James Webb's data might force us to rewrite the very first chapter of existence itself. But that's just the beginning of what we found staring back at us from the cosmic dawn. 400 million years after the Big Bang, the universe should have been a cosmic wasteland. Think of it like this. If the entire history of the cosmos was compressed into 1 year, we're looking at January 2nd. At that point, galaxies should be tiny, primitive collections of the very first stars. What James Webb found instead were massive, mature galaxies that looked like they'd been around for billions of years. These aren't small collections of newborn stars struggling to survive. We're seeing galaxies with masses equivalent to 100 billion suns, perfectly organized into spiral arms and central bulges. To put this in perspective, our own Milky Way galaxy took over 13 billion years to reach this level of development. Yet here are galaxies that somehow achieved this complexity when the universe was barely out of diapers. The numbers don't add up. Computer simulations show that galaxies this massive should take at least 2 billion years to form through the slow process of smaller galaxies merging together. But we're seeing them when the universe was only 400 million years old. It's like finding a fully grown oak tree in a garden that was planted yesterday. Dr. Ivo Labbé from Swinburne University described these discoveries as galaxy monsters that shouldn't exist. His team found galaxies so massive they make up almost as much matter as all the stars that should exist in the entire observable universe at that time. The math simply doesn't work with our current understanding of cosmic evolution. Even more puzzling is how organized these galaxies appear. The Big Bang Theory predicts that early galaxies should be chaotic and irregular, slowly forming structure through gravitational interactions over cosmic time. Instead, James Webb is showing us galaxies with clear spiral patterns, central black holes, and organized star formation regions. These are features that should take billions of years to develop. This discovery is forcing astronomers to confront an uncomfortable possibility. Either our understanding of how fast galaxies can form is completely wrong, or our timeline of cosmic history needs a major revision. Some scientists are beginning to whisper about alternative theories that could explain these observations, but accepting those alternatives means abandoning much of what we thought we knew about the universe. The implications stretch beyond just galaxy formation. If massive galaxies existed this early, they would have influenced the entire structure of cosmic evolution. The gravitational effects of these monster galaxies should have left traces throughout the universe that we simply don't see in other observations. Yet the evidence keeps mounting that these impossible galaxies are absolutely real. In the beginning, the universe knew only 3 elements: hydrogen, helium, and tiny traces of lithium. Every other element in the periodic table had to be forged inside the nuclear furnaces of stars and scattered through space when those stars died. This process takes time, billions of years. Yet James Webb is finding heavy elements in galaxies that formed when the cosmos was still a cosmic infant. Picture a star as a cosmic kitchen. It starts with simple ingredients, hydrogen and helium, and slowly cooks them into heavier elements through nuclear fusion. Carbon, oxygen, silicon, iron. All these elements require multiple generations of stars to create. The first stars had to live their entire lives, explode as supernovas, and seed space with heavy elements before the next generation could form planets and more complex chemistry. This stellar cooking process is like a cosmic assembly line that shouldn't be rushed. The most massive stars burn through their fuel quickly and explode within a few million years. But even the fastest cosmic assembly line needs hundreds of millions of years to produce significant amounts of heavy elements. The universe at 400 million years old simply hadn't had enough time for this process to work. Yet spectroscopic analysis of these early galaxies shows clear signatures of oxygen, carbon, and even heavier elements like silicon and magnesium. The concentrations aren't trace amounts that might be explained by unusually fast stellar evolution. We're seeing metal abundances that suggest multiple generations of star formation and death had already occurred. Dr. Emma Curtis Lake, who led some of these observations, described finding galaxies with metallicities that rival much younger systems. The spectral lines don't lie. These galaxies contain elements that shouldn't exist in such quantities for billions more years of cosmic evolution. The discovery creates a cascade of problems for our cosmic timeline. If heavy elements existed this early, then planet formation could have begun much sooner than predicted. Rocky planets like Earth require these heavier elements to form. The implications for when life might have first appeared in the universe become staggering. Some astronomers are proposing that the very first stars might have been much more massive than we thought, burning through their lives and creating heavy elements at unprecedented rates. Others suggest that star formation itself might work differently in the early universe than it does today. But both explanations require us to revise fundamental assumptions about stellar physics. The elements James Webb found shouldn't exist yet, but they're there, written in the light of ancient galaxies, challenging everything we thought we knew about cosmic chemistry. What we discovered next makes this element problem look simple by comparison. Imagine trying to build a skyscraper during an earthquake while blindfolded. That's what galaxy formation should have looked like in the early universe. The cosmos was violent, chaotic, and filled with dark matter and gas crashing together in random collisions. Galaxies should have grown slowly and messily through countless mergers over billions of years. What James Webb found instead were galaxies that looked like they'd been designed by a cosmic architect. The Hubble Space Telescope had already shown us that distant galaxies appear more irregular and chaotic than nearby ones. This made perfect sense. We were looking back in time to see galaxies in their awkward teenage years, still growing and organizing themselves. James Webb was supposed to push even further back, to see cosmic toddlers stumbling around in the dark. Instead, we found galaxies with clear spiral arms, organized central bulges, and structured star formation patterns. These features require delicate gravitational balance and billions of years of quiet evolution to develop. In our own cosmic neighborhood, only the most mature galaxies display such perfect organization. Yet here they were, in the cosmic dawn, looking impossibly sophisticated. Dr. Stephen Finkelstein from the University of Texas described these discoveries as finding adult galaxies in a cosmic nursery. The level of organization defies everything we know about hierarchical structure formation, which predicts that small objects merge to form larger ones over cosmic time. These galaxies appear to have skipped their messy childhood entirely. The smooth disk structures are particularly puzzling. In today's universe, galaxy disks form through a complex process where gas settles into rotating patterns over hundreds of millions of years. Early in cosmic history, frequent mergers and chaotic conditions should prevent such delicate structures from surviving. Yet James Webb is showing us pristine spiral patterns that look like they've never been disturbed. Even more mysterious are the central supermassive black holes that seem to be perfectly coordinated with their surrounding galaxies. In the modern universe, we observe tight correlations between black hole masses and the properties of their host galaxies. This relationship takes billions of years to establish through a complex dance of feedback between star formation and black hole growth. Finding such coordination in young galaxies suggests processes we don't understand. The implications challenge the entire concept of cosmic evolution. If galaxies can organize themselves this quickly, then our understanding of how structure forms in the universe needs a complete overhaul. The smooth, organized galaxies James Webb discovered shouldn't exist for billions more years. But their perfect spiral arms are just spinning us toward an even stranger discovery about rotation speeds that break the laws of physics. Galaxies rotate like cosmic hurricanes, held together by the gravitational embrace of dark matter halos that surround them like invisible cocoons. The faster a galaxy spins, the more mass it needs to prevent itself from flying apart. This relationship between rotation speed and mass is one of the most reliable rules in astronomy. But James Webb found ancient galaxies spinning so fast they should have torn themselves to pieces billions of years ago. When astronomers measure how fast stars move in galaxy disks, they can calculate exactly how much total mass the galaxy contains. It's like watching cars on a circular racetrack. The faster they go without flying off, the steeper the banking must be. In galaxies, that banking comes from gravitational mass, mostly in the form of dark matter. The problem is that these early galaxies are rotating at speeds that require dark matter halos much more massive than anything we see in computer simulations of structure formation. Some galaxies are spinning at 300 kilometers per second, when they should be limited to maybe 150. That's like finding a motorcycle taking a tight turn at twice the speed that should send it skidding into the wall. Dr. Claude-André Faucher-Giguère from Northwestern University has been studying these rotation curves and describes them as impossible under current models of galaxy formation. The dark matter halos required to stabilize such rapid rotation would be so massive they should dominate the entire region of space around them. Yet we don't see evidence for such monster halos in the cosmic web structure. Even stranger is how quickly these rotation patterns must have established themselves. In today's universe, galaxy disks build up their rotation gradually, as gas settles into stable orbits over hundreds of millions of years. But these ancient galaxies appear to have reached maximum spin almost immediately after forming. It's like finding a figure skater already in a perfect pirouette the moment they step onto the ice. The physics gets even more problematic when you consider angular momentum conservation. As galaxies form from collapsing gas clouds, They should spin up gradually as they shrink, like a figure skater, pulling in their arms. But the rotation speeds James Webb measured suggest these galaxies started with far more angular momentum than the cosmic web should have been able to provide. Some theorists are proposing exotic solutions involving modified gravity or alternative dark matter models. Others suggest that early galaxy formation might involve processes we've never considered. But every explanation requires abandoning well-tested physics or accepting that the early universe operated under completely different rules. These spinning galaxies are rotating us toward an even more disturbing discovery about collisions that happened before galaxies should even exist. Galaxy mergers are cosmic train wrecks that unfold over hundreds of millions of years. When two galaxies collide, their gravitational dance creates tidal tails, stellar streams, and distorted structures that astronomers can recognize, like forensic evidence at a crime scene. James Webb found this evidence in galaxies that formed when the universe was so young that collisions shouldn't have been possible yet. The timeline problem is severe. According to our models, the first galaxies were tiny, isolated islands of stars scattered across vast distances. They were like cosmic hermits, too far apart and too small to interact with each other significantly. Major galaxy mergers should have waited until the universe was at least 1 billion years old, when structures had grown large enough and close enough to gravitationally influence each other. Yet James Webb is showing us clear merger signatures in galaxies from just 400 million years after the Big Bang. We see tidal streams of stars pulled away from galactic cores, double nuclei indicating recent collisions, and asymmetric structures that can only result from gravitational encounters between massive objects. Dr. John Silverman from the Kavli Institute has been analyzing these early merger signatures and describes them as finding car crashes in a world where cars haven't been invented yet. The morphological features are unmistakable. These galaxies have definitely collided with other massive systems, but the cosmic timeline says such collisions should be impossible this early in universal history. The discovery gets more puzzling when you consider the merger rates. In the local universe, major galaxy mergers are relatively rare events. A galaxy like the Milky Way might experience one significant merger every few billion years. But in these early observations, merger signatures appear in almost every galaxy James Webb examines. It's as if the young universe was experiencing a collision epidemic. Even more problematic is the scale of these ancient mergers. We're not seeing small galaxies absorbing tiny companions. These are major mergers between systems that are already massive and well-developed. The energy required to disrupt such large galaxies and then reorganize them into the structures we observe should take billions of years. Yet we're seeing the aftermath when the universe was barely 500 million years old. The implications cascade through our understanding of cosmic evolution. If major mergers were common this early, they would have triggered massive bursts of star formation and fed central black holes at unprecedented rates. This should have left observable signatures throughout the universe that we simply don't see in other measurements of cosmic history. Some astronomers are beginning to question whether our fundamental timeline of structure formation is completely wrong. Maybe the universe organized itself much faster than we ever imagined possible. But the evidence for impossible timing doesn't stop with galaxy collisions. Next, we discovered something even more fundamentally challenging about the cosmic microwave background itself. The cosmic microwave background is like the universe's baby picture, a snapshot of what the cosmos looked like just 380,000 years after the Big Bang. This ancient light carries the imprint of tiny density fluctuations that would eventually grow into galaxies, stars, and everything we see today. But James Webb's observations suggest that baby picture might be telling us the wrong story about how the universe actually developed. The cosmic microwave background shows us a universe that was remarkably smooth and uniform in its early days. The density variations were incredibly small, just 1 part in 100,000. These tiny ripples in the cosmic fabric were like seeds that would slowly grow through gravitational attraction over billions of years into the large-scale structures we observe today. Cosmologists have used sophisticated computer simulations to grow these seeds forward in time, predicting exactly what the universe should look like at any given epoch. The models are incredibly detailed, tracking how dark matter clumps, how gas flows, and how stars form. These simulations confidently predict that at the time James Webb is observing, galaxies should be small, irregular, and relatively rare. But that's not what we're seeing. The massive, organized galaxies James Webb discovered require initial density fluctuations much larger than what the cosmic microwave background recorded. It's like finding full-grown trees in a field where the soil analysis says only grass seeds were planted. Dr. Rajesh Mainali from the University of California has been comparing James Webb observations with cosmic microwave background predictions and describes the mismatch as fundamentally problematic. The early universe appears to have had far more structure-forming power than the baby picture suggests was possible. The discrepancy isn't subtle. Some of the galaxies James Webb found are so massive that they require regions of space that were overdense by factors the cosmic microwave background says should not exist. The statistical probability of such massive galaxies forming from the observed initial conditions is essentially zero. This creates a paradox that strikes at the heart of cosmology. Either our interpretation of the cosmic microwave background is wrong, or our understanding of how structures grow from initial fluctuations needs a complete revision. Both possibilities would require abandoning fundamental assumptions about cosmic evolution. Some theorists are exploring exotic solutions involving primordial black holes, modified gravity, or completely alternative scenarios for the early universe. Others suggest that the cosmic microwave background might not be the pristine record of initial conditions we thought it was. The mismatch between our cosmic baby picture and what James Webb actually found growing in the universe is pushing us toward an even more disturbing discovery about black holes that grew impossibly fast. Quasars are the universe's most powerful lighthouses, powered by supermassive black holes that consume matter at extraordinary rates and blast energy across billions of light years. These cosmic monsters contain millions or billions of times the mass of our Sun. But James Webb found fully grown quasars shining when the universe was so young that black holes should have barely begun their journey towards such enormous sizes. Building a supermassive black hole is like constructing a skyscraper one grain of sand at a time. The process requires patience and lots of raw material. Even under ideal conditions, black holes can only grow so fast because the energy they release while feeding heats up and pushes away the very matter they're trying to consume. This natural speed limit means that even the hungriest black holes need billions of years to reach supermassive proportions. The physics is unforgiving. When matter falls into a black hole, it heats up and glows brightly before disappearing forever. This radiation pressure acts like a cosmic traffic cop, regulating how much material can approach the black hole at any given time. The maximum growth rate, called the Eddington limit, means that even a black hole that starts with the mass of 1,000 suns would need over 1 billion years to reach the billion solar mass range. Yet James Webb discovered quasars powered by billion solar mass black holes when the universe was only 600 million years old. These aren't modest black holes still growing toward maturity. They're fully developed supermassive objects already dominating their galactic environments and powering some of the brightest objects in the cosmos. Dr. Xiaohui Fan from the University of Arizona has been studying these early quasars and describes them as finding adult elephants in a nursery full of mice. The growth rates required to explain these observations exceed theoretical limits by factors of 10 or more. Either our understanding of black hole physics is incomplete, or these black holes started much larger than anything our models predict. The discovery becomes even more puzzling when you consider where these black holes came from originally. The very first black holes should have formed from the collapse of the first generation of stars, which themselves took tens of millions of years to form and evolve. This means the seed black holes that would eventually become supermassive should have started with masses equivalent to maybe 100 suns at most. Getting from 100 solar masses to 1 billion solar masses in 600 million years while respecting the Eddington limit is mathematically impossible. It's like trying to drive from New York to Los Angeles in 1 hour, while obeying the speed limit. Some theorists are proposing that the first black holes might have formed through completely different mechanisms, starting with much larger initial masses. Others suggest that black hole growth in the early universe might not obey the same physical limits we observe today. But these impossibly massive black holes are feeding star formation. Stars are born in cosmic nurseries called molecular clouds, where gravity slowly compresses gas and dust until nuclear fusion ignites. This process has natural speed limits built into the physics of how matter behaves under extreme conditions. But James Webb found galaxies forming stars at rates so fast they violate every theoretical maximum we've calculated for stellar birth. In today's universe, even the most active star-forming galaxies convert only about 1% of their gas into stars every million years. This efficiency limit exists because star formation is a messy, wasteful process. When massive stars form, they blow powerful winds and eventually explode as supernovas, heating up and dispersing the surrounding gas. This stellar feedback acts like a cosmic thermostat, regulating how quickly new stars can form. The most extreme star-forming galaxies we observe today create about 1,000 new stars per year. This rate is already considered extraordinary and unsustainable. Galaxies forming stars this quickly will exhaust their gas supplies within a few 100 million years. Yet James Webb discovered early galaxies with star formation rates exceeding 10,000 stars per year, sustained over periods that should have been impossible. Dr. Pascal Oesch from the University of Geneva has been analyzing these stellar birth rates and describes them as finding cosmic factories running at 10 times their maximum rated capacity. The energy output from such intense star formation should heat up and expel all the remaining gas, shutting down further stellar birth almost immediately. Yet these galaxies appear to maintain extreme star formation rates for hundreds of millions of years. The physics becomes even more problematic when you consider the raw materials required. Forming 10,000 stars per year requires consuming gas at rates that would exhaust even the largest reservoirs within a cosmic blink of an eye. These galaxies would need constant resupply of fresh material from their surroundings, but the early universe was much less dense than today, making such massive gas flows unlikely. Even more puzzling is how these galaxies managed to retain their star-forming gas in the first place. The intense radiation from rapid star formation should create powerful galactic winds that blow gas out of the galaxy entirely. We observe this process in local starbursts, where stellar feedback eventually quenches star formation. But these early galaxies seem immune to their own stellar violence. The discovery suggests that star formation in the early universe operated under completely different rules than what we observe today. Maybe the gas was denser, the stellar feedback less effective, or the entire process of stellar birth fundamentally different when the cosmos was young. Some astronomers are proposing exotic mechanisms involving primordial gas with unusual properties or gravitational conditions that no longer exist in the modern universe. Others suggest that our understanding of stellar feedback and gas dynamics needs major revision. But these impossible star formation rates are organizing themselves into structures that challenge our understanding of cosmic evolution itself. The early universe should have been cosmic chaos, a violent, turbulent place where matter crashed together randomly as gravity tried to organize the aftermath of the Big Bang. Large-scale structure should have emerged slowly and messily over billions of years through countless random collisions and mergers. But James Webb found a level of cosmic organization that suggests the universe knew exactly what it was doing from the very beginning. Picture the cosmic web as a three-dimensional spider web stretching across billions of light years, with galaxies strung along filaments of dark matter like dewdrops on silk strands. This web structure is one of the most beautiful and organized features of the modern universe. Computer simulations show that it should take at least 1 billion years for such organized patterns to emerge from the smooth initial conditions after the Big Bang. Yet James Webb is revealing hints of large-scale structure and organized galaxy distributions in the cosmic dawn. when the universe was only a few 100 million years old. We're seeing aligned galaxy clusters, coordinated star formation patterns across vast distances, and gravitational influences between objects that should still be isolated islands in space. Dr. Casey Popovich from Texas A&M University has been mapping these early large-scale structures and describes them as finding a completed jigsaw puzzle when you expected to see scattered pieces still looking for their places. The level of gravitational coordination between distant objects requires a cosmic web that developed far faster than our models predict. The organization appears at multiple scales simultaneously. Not only are individual galaxies more structured than expected, but they're also organized into groups and clusters that shouldn't have had time to form. The gravitational binding energy required to hold such systems together suggests they assembled much more quickly and efficiently than hierarchical structure formation allows. Even more mysterious is how these organized structures maintain their coherence across such vast distances. In the early universe, light hadn't had enough time to travel between widely separated regions, meaning they couldn't coordinate their behavior through any known physical mechanism. Yet we're seeing correlated properties across scales that should be causally disconnected. This cosmic organization problem strikes at fundamental assumptions about how the universe evolved from smooth initial conditions to the structured cosmos we observe today. If large-scale structure formed this quickly, it suggests processes or initial conditions completely different from what the Big Bang Theory predicts. Some cosmologists are exploring ideas about cosmic phase transitions, primordial magnetic fields, or exotic forms of dark energy that could accelerate structure formation. Others are questioning whether the initial conditions after the Big Bang were as smooth and random as we've assumed. But this organized cosmic architecture is supporting planetary systems that formed impossibly early in cosmic history. Rocky planets like Earth require a cosmic recipe that takes billions of years to prepare. You need multiple generations of stars to forge heavy elements, supernova explosions to scatter those elements through space, and then slow gravitational processes to gather dust and debris into solid worlds. But James Webb found evidence of planetary systems in galaxies so young that the ingredients for rocky planets shouldn't even exist yet. Planet formation is like cosmic cooking that can't be rushed. The first stars contained only hydrogen and helium, the simplest elements forged in the Big Bang itself. Every heavier element, the carbon in our bodies, the oxygen we breathe, the silicon in Earth's rocks, the iron in our blood, had to be manufactured inside stellar cores and distributed by stellar death. This element production takes time. Even after heavy elements become available, building planets is a slow process. Tiny dust grains must stick together to form pebbles. Pebbles clump into boulders. Boulders accumulate into asteroids, and asteroids collide to build planets over tens of millions of years. The entire sequence from stellar death to rocky planet formation typically requires at least 1 billion years of cosmic evolution. Yet spectroscopic analysis of some early galaxies shows absorption features that could indicate dust and potentially even planetary debris in systems that formed when the universe was less than 800 million years old. Dr. Kevin Heng from the University of Bern describes these observations as finding evidence of planetary construction in a cosmic era when the building materials shouldn't even exist. The implications cascade through our understanding of when life might have first appeared in the universe. If rocky planets could form this early, then the conditions for biology might have existed billions of years sooner than we ever imagined. The universe could have been teeming with potentially habitable worlds when our own solar system was still just a distant dream. Even more intriguing are hints of atmospheric absorption in some of these early systems. While we can't yet definitively confirm planetary atmospheres in such distant and ancient objects, the spectral signatures suggest complex chemistry involving heavy elements arranged in ways that look suspiciously like atmospheric processes. The discovery forces us to reconsider how quickly planetary systems can assemble and begin operating as complex chemical laboratories. Maybe dust grain sticking was more efficient in the early universe, or gravitational processes worked faster in the denser environment of cosmic youth. Some astronomers are proposing that the first planetary systems might have formed through mechanisms we don't observe in the modern universe, perhaps involving primordial materials or gravitational conditions that no longer exist today. But these rapidly forming planetary systems are challenging our understanding of the cosmic inflation theory itself. Cosmic inflation theory proposes that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang, stretching space faster than light and smoothing out any initial irregularities. This inflation should have created a universe with very specific properties. See, smooth on, large scales, with tiny, precisely characterized fluctuations that would slowly grow into cosmic structure. But James Webb's discoveries suggest the universe might not have followed inflation's script at all. Inflation theory makes testable predictions about what the early universe should look like. The density fluctuations that eventually became galaxies should have specific statistical properties, following patterns that reflect the quantum mechanical processes that created them during the inflationary epoch. These fluctuations should be small, nearly scale invariant, and distributed according to precise mathematical relationships. The problem is that the massive, organized structures James Webb discovered require initial fluctuations much larger and more organized than inflation predicts. The theory suggests that regions of space dense enough to form the observed massive galaxies should be extraordinarily rare, so rare that we shouldn't see any in the cosmic volumes James Webb can observe. Dr. Paul Steinhardt from Princeton University, one of inflation theory's architects, who later became a critic, describes these observations as potentially fatal problems for the inflationary paradigm. The statistical properties of the early galaxies don't match what inflation theory predicts should emerge from quantum fluctuations during exponential expansion. Even more problematic is the coherent organization of structure across vast scales. Inflation theory predicts that different regions of space should have evolved independently after the rapid expansion separated them beyond any possible causal connection. Yet James Webb observations hint at coordinated properties across distances that should be completely independent according to inflationary cosmology. The discovery forces cosmologists to confront uncomfortable questions about whether cosmic inflation actually occurred, or whether it worked differently than our models suggest. Alternative theories that never required inflation are gaining renewed attention as potential explanations for James Webb's observations. Some theorists are exploring bouncing universe models, where our cosmos emerged from the collapse and rebound of a previous universe, potentially preserving organizational information that inflation would have erased. Others are investigating modified gravity theories or exotic forms of dark energy that could create the observed structure without requiring inflationary expansion. The implications reach far beyond cosmology, into fundamental physics. Inflation theory has been intimately connected with theories of quantum gravity and the earliest moments of cosmic history. If inflation is wrong, it suggests our understanding of physics at the most fundamental level needs major revision. But as multiple independent observations point to the same problems, the evidence becomes impossible to ignore. Science advances through the accumulation of evidence, and isolated anomalies can often be explained away by measurement errors, statistical flukes, or incomplete understanding. But when multiple independent observations using different techniques all point to the same fundamental problem, the scientific community must confront the possibility that accepted theories are simply wrong. James Webb's discoveries represent exactly this kind of converging evidence crisis. The telescope didn't find just one type of anomaly. It discovered massive galaxies where small ones should exist, heavy elements that form too quickly, organized structures that should be chaotic, rotation speeds that violate physics, collision signatures that predate possible interactions, star formation rates that break theoretical limits, and planetary systems that assembled impossibly fast. Each discovery alone might be dismissed as an outlier, but together they paint a consistent picture of a universe that doesn't follow our rules. Independent research teams using different analysis methods have confirmed these findings repeatedly. Dr. Ivo Labé's galaxy mass measurements have been verified by multiple groups, using completely different techniques. Spectroscopic evidence for early heavy elements has been detected by several independent surveys. The impossible rotation speeds have been confirmed through both direct velocity measurements and gravitational lensing studies. Even more compelling is how these diverse anomalies all point in the same direction toward a universe that organized itself much faster and more efficiently than the Big Bang Theory predicts. The problems aren't random scattered inconsistencies that might be explained by minor theoretical adjustments. They form a coherent pattern suggesting our fundamental timeline of cosmic evolution is wrong. The statistical weight of accumulated evidence is becoming overwhelming. When astronomers calculate the probability that all these observations could be explained by measurement errors or rare statistical fluctuations, the numbers become vanishingly small. We're not looking at unlucky coincidences, we're seeing systematic discrepancies that demand explanation. This convergence of evidence is forcing theoretical physicists to abandon incremental modifications to existing theories and consider revolutionary alternatives. Dr. Sakestein, Subir Sarkar from Oxford University describes the situation as a paradigm crisis where accumulated anomalies can no longer be accommodated within the existing theoretical framework. The process mirrors historical scientific revolutions, where multiple independent observations eventually forced complete theoretical overhauls. Just as the discovery of stellar parallax, galactic redshifts, and cosmic microwave background radiation converged to establish the Big Bang Theory, James Webb's discoveries might be converging to overthrow it. Scientific institutions are beginning to acknowledge that the discrepancies require serious theoretical attention rather than ad hoc explanations. Major funding agencies are directing resources toward alternative cosmological models that could explain James Webb's observations without violating fundamental physics. The accumulated weight of evidence is pushing theoretical physicists toward completely new models of cosmic evolution. Behind closed doors in physics departments around the world, theorists are working frantically to develop alternative cosmological models that could explain James Webb's impossible observations without breaking the laws of physics. These aren't minor adjustments to existing theories. They're revolutionary new frameworks that could replace the Big Bang Theory entirely. The quiet urgency of this theoretical work reflects how seriously physicists are taking the mounting evidence crisis. Dr. Neil Turok from the Perimeter Institute has been developing cyclic cosmology models where the universe undergoes infinite cycles of expansion and contraction, with each cycle preserving organizational information that could explain the rapid structure formation James Webb observed. These models suggest our universe might not have had a beginning at all, but rather emerged from the organized collapse of a previous cosmic cycle. Meanwhile, Dr. João Magejo from Imperial College London is exploring variable speed of light cosmologies, where the fundamental constants of physics were different in the early universe. If light traveled faster in cosmic youth, it could allow widely separated regions to coordinate their evolution, explaining the large-scale organization James Webb discovered without requiring impossible timescales. Modified gravity theorists like Dr. Sabine Hossenfelder are investigating whether gravitational physics itself works differently on cosmic scales or in extreme environments. If gravity was stronger or operated through additional dimensions in the early universe, structure formation could proceed much faster than general relativity predicts, naturally explaining the mature galaxies James Webb found. Even more radical are theories involving multiple universes or higher dimensional physics. Some models suggest our observable cosmos might be embedded in a larger multiverse structure, with matter and energy flowing between connected regions through mechanisms we don't yet understand. These scenarios could provide the additional organizational power needed to explain rapid cosmic evolution. Dr. Paul Frampton from the University of North Carolina has been exploring bouncing cosmologies, where dark energy cycles between expansion and contraction phases, creating periods of accelerated structure formation that could explain James Webb's observations. These models abandon the idea of a single Big Bang in favor of multiple cosmic epochs with different physical properties. The theoretical work is proceeding with unusual urgency because the observational evidence continues mounting faster than explanations can be developed. Each new James Webb discovery adds constraints that eliminate more traditional explanations, forcing theorists toward increasingly exotic alternatives. What makes this theoretical revolution particularly significant is how it's happening across multiple subdisciplines simultaneously. Cosmologists are revising models of cosmic evolution. Particle physicists are questioning fundamental constants, and astrophysicists are reconsidering stellar and galactic formation processes. The James Webb crisis is forcing a coordinated rethinking of physics itself. Some of the most promising new models involve what physicists call emergent gravity, the idea that gravitational attraction might not be fundamental, but rather emerge from more basic quantum mechanical processes. If gravity works differently than we thought, it could explain why cosmic structures form so much faster than our current theories predict. But these new theoretical frameworks are approaching a tipping point where they might fundamentally change our understanding of time and space itself. Einstein's theory of relativity taught us that space and time are woven together into a single fabric called space-time, which can be stretched, warped, and curved by matter and energy. This understanding has been tested countless times and forms the foundation of modern cosmology. But James Webb's discoveries are forcing physicists to question whether space-time itself might work differently than we've assumed, especially in the extreme conditions of the early universe. The problem isn't just that galaxies formed faster than expected, it's that they formed in ways that seem to violate causality itself. Structure formation requires information to travel between different regions of space so they can coordinate their gravitational behavior. But in the early universe, many of the organized structures James Webb discovered are separated by distances that light hadn't had time to cross, making coordination impossible under our current understanding of space-time. Dr. Lee Smolin from the Perimeter Institute has been exploring theories where time itself might be emergent rather than fundamental. In these models, what we experience as the flow of time could be an approximate description that breaks down under extreme conditions. If time worked differently in the early universe, it could allow processes that seem impossible under our current physics. Even more radical are theories suggesting that space might have additional dimensions that were accessible in cosmic youth but became hidden as the universe evolved. Extra-dimensional models could provide pathways for information and energy to travel faster than light in our three-dimensional space, explaining the impossible coordination James Webb observed. Some physicists are investigating whether the speed of light itself might not be constant across cosmic history. If light traveled faster in the early universe, it would allow widely separated regions to communicate and coordinate their evolution, naturally explaining the large-scale organization that formed too quickly under current physics. Dr. Carlo Rovelli from the French National Center for Scientific Research has developed loop quantum gravity theories, where space-time itself is quantized, made up of discrete units rather than being continuous. In these models, the fabric of space-time might behave very differently under the extreme conditions of the early universe, allowing structure formation processes that are impossible in classical space-time. The implications reach far beyond cosmology into the nature of reality itself. If our understanding of time and space is fundamentally wrong, it affects everything from quantum mechanics to the possibility of time travel. The James Webb discoveries might be showing us that the universe operates according to physics we haven't discovered yet. These space-time theories are converging on a disturbing possibility that the Big Bang might not have been the beginning of everything after all. For nearly a century, the Big Bang has been more than just a scientific theory. It's been our origin story, the ultimate answer to the question of where everything came from. But James Webb's discoveries are forcing us to confront the possibility that the Big Bang might not have been the beginning of everything, but rather just one event in a much larger cosmic story that we're only beginning to understand. The evidence is pointing toward a universe that was already organized and structured when the Big Bang occurred. The massive galaxies, heavy elements, and coordinated structures James Webb discovered suggest that cosmic evolution didn't start from a smooth, uniform beginning. Instead, they hint at a universe that inherited organizational information from whatever came before. Dr. Ana Ijaz from New York University has been developing models where the Big Bang emerges from the collapse and bounce of a previous universe. In these scenarios, the organized structures James Webb observed could be fossils of cosmic evolution that preceded our current expansion phase. The universe might undergo infinite cycles of expansion, contraction, and rebirth, with each cycle preserving information from the previous one. Even more revolutionary are theories suggesting that multiple universes might exist simultaneously, with matter and energy flowing between them through mechanisms we don't understand. If our observable cosmos is connected to a larger multiverse, it could explain where the organizational power for rapid structure formation came from. It was borrowed from neighboring universes. Some physicists are exploring the possibility that the Big Bang was actually a phase transition rather than a creation event. Just as water can transition from ice to liquid to vapor while remaining the same fundamental substance, the universe might have transitioned from one physical state to another without actually beginning to exist. Dr. Abhay Ashtekar from Pennsylvania State University has developed loop quantum cosmology models, where the Big Bang is replaced by a big bounce, a transition from a contracting phase to an expanding phase of cosmic evolution. In these models, the universe has no beginning or end, but rather undergoes eternal cycles of expansion and contraction. The philosophical implications are staggering. If the Big Bang wasn't the beginning, then questions about what came before it become scientifically meaningful rather than metaphysical speculation. The universe might be infinitely old, with our current expansion phase being just one chapter in an eternal story. This possibility challenges not just cosmology, but our entire understanding of causation, existence, and the nature of reality itself. If the universe has always existed in some form, it changes how we think about everything from the origins of physical laws to the possibility of life existing in previous cosmic cycles. The James Webb discoveries might be showing us that we're not the first chapter of cosmic evolution, but rather the latest chapter in an infinite book. The scientific revolution brewing in cosmology isn't just about adjusting details or fine-tuning existing theories. James Webb's discoveries are approaching a critical threshold where the accumulated evidence might force the complete abandonment of our current cosmic origin story in favor of something entirely different. We're standing at the edge of a paradigm shift that could rival the Copernican revolution in its scope and implications. The tipping point comes when anomalies can no longer be explained by modifying existing theories. In the history of science, this moment arrives when multiple independent lines of evidence converge on the same conclusion, that the fundamental assumptions underlying accepted theory are simply wrong. The James Webb discoveries are rapidly approaching this critical mass of contradictory evidence. Dr. Subir Sarkar from Oxford University describes the current situation as a crisis of epic proportions in cosmology. The standard model of cosmic evolution requires increasingly exotic modifications to accommodate each new James Webb observation. Dark energy must be more complex. Dark matter must behave differently. Inflation must work in ways we never imagined. And stellar physics must operate under completely different rules in the early universe. The mathematical contortions required to save the Big Bang theory are becoming so elaborate that many physicists are questioning whether it's time to abandon the theory entirely, rather than continue patching it with increasingly implausible modifications. It's reaching the point where the cure is becoming worse than the disease. Major scientific institutions are beginning to acknowledge the severity of the crisis. The European Space Agency has approved funding for missions specifically designed to test alternative cosmological models. The National Science Foundation has created new funding categories for research into non-standard cosmologies. These institutional responses reflect growing recognition that the James Webb discoveries represent more than just interesting anomalies. The convergence of evidence is accelerating. Every few months, new James Webb observations add to the pile of inexplicable data. The statistical probability that all these anomalies could be explained by measurement errors or theoretical oversights is approaching zero. The universe James Webb is revealing simply doesn't match the universe our theories predict. Historical precedent suggests we're approaching the moment when the scientific community will be forced to choose between increasingly implausible explanations for the existing theory and revolutionary new models that naturally explain the observations. The Ptolemaic system of planetary motion required increasingly complex epicycles to match observations until Copernicus proposed that the Sun, not Earth, was the center of the solar system. We might be witnessing a similar moment in cosmology. The Big Bang Theory is requiring increasingly complex modifications to match James Webb's observations. Alternative theories that seemed radical just a few years ago are beginning to look like natural explanations for what we're actually seeing. The next few years of James Webb observations will likely determine whether we're looking at the end of the Big Bang era in cosmology and the beginning of something completely new. The story of how the universe began isn't just a scientific theory. It's the foundation of how we understand our place in existence itself. If James Webb's discoveries force us to abandon the Big Bang Theory and embrace a completely different cosmic origin story, the implications will cascade through every aspect of human knowledge, from philosophy and religion to our most basic sense of meaning and purpose. Throughout history, changes in our cosmic story have triggered profound shifts in human consciousness. When Copernicus showed that Earth wasn't the center of the universe, it didn't just change astronomy, it revolutionized philosophy, religion, and humanity's sense of its own importance. When Darwin revealed that life evolved rather than being specially created, it transformed not just biology, but our entire understanding of what it means to be human. The James Webb revolution promises to be even more fundamental. If the universe has always existed in some form, with no ultimate beginning, it challenges basic assumptions about causation, creation, and the nature of existence itself. The questions that have driven human inquiry for millennia — why is there something rather than nothing? What came before the beginning? What is our cosmic purpose? — would need to be completely reframed. Dr. Carlo Rovelli from the French National Center for Scientific Research argues that major scientific revolutions always force us to reconstruct our understanding of reality from the ground up. The James Webb discoveries aren't just challenging cosmology, they're challenging the conceptual frameworks we use to understand existence itself. If the universe operates according to physics we haven't discovered yet, with time and space working differently than we assumed, it opens possibilities we can barely imagine. Maybe consciousness plays a role in cosmic evolution. Maybe information is more fundamental than matter and energy. Maybe the universe is stranger and more wonderful than our current theories suggest. The implications extend to the possibility of life itself. If rocky planets and complex chemistry emerged billions of years earlier than previously thought, the universe might have been teeming with life when our solar system was still just a distant possibility. We might not be among the first intelligent beings to contemplate the cosmos, but rather the latest in an unimaginably long chain of cosmic evolution. Even our understanding of death and time could be transformed. If the universe undergoes eternal cycles of expansion and contraction, with information preserved across cosmic phases, it raises profound questions about whether anything is ever truly lost. The James Webb discoveries might be showing us a universe where existence itself is eternal and indestructible. The psychological adjustment to a completely new cosmic story will be challenging. Humans have always needed origin stories to provide meaning and context for their lives. The Big Bang Theory, for all its scientific precision, also served as a modern creation myth that helped people understand their place in the cosmos. But perhaps the most profound implication is that the James Webb discoveries remind us how much we still don't know. The universe continues to surprise us, revealing new mysteries just when we thought we had everything figured out. The greatest discovery might not be any specific new theory, but rather the humbling recognition that the cosmos is far stranger, more complex, and more wonderful than we ever imagined. The James Webb Space Telescope was built to confirm our understanding of cosmic origins. Instead, it might be showing us that the greatest adventures in understanding are still ahead of us, waiting to be discovered in the infinite mystery of existence itself. We set out to prove our cosmic origin story with the most powerful telescope ever built, expecting to find confirmation of everything we thought we knew about the universe. Instead, James Webb showed us galaxies that shouldn't exist, stars that form too quickly, and structures too organized for cosmic youth. The telescope that was meant to be the ultimate witness to the Big Bang might instead be writing its obituary. The evidence is overwhelming and undeniable. Massive galaxies in cosmic infancy, heavy elements that formed impossibly fast, rotation speeds that break physics, collision signatures that predate possible interactions, star formation rates beyond theoretical limits, and planetary systems that assembled before their ingredients should exist. Each discovery alone might be explained away, but together, they paint a picture of a universe that refuses to follow our rules. This isn't just a crisis in cosmology. It's a revolution in our understanding of reality itself. The accumulated weight of James Webb's observations is forcing physicists to question not just when the universe began, but whether it had a beginning at all. We might be witnessing the end of the Big Bang era and the birth of a completely new cosmic story. The implications cascade through every aspect of human knowledge. If time and space work differently than we assumed, if the universe has always existed in some form, if cosmic evolution operates according to physics we haven't discovered yet, then everything we thought we knew about existence needs to be reconsidered. The questions that have driven human inquiry for millennia must be completely reframed. But perhaps the most profound discovery is how much mystery remains. The universe continues to surprise us, revealing new wonders just when we thought we had everything figured out. The James Webb observations remind us that the cosmos is far stranger, more complex, and more wonderful than our theories suggest. The greatest scientific revolutions in history began with observations that didn't fit existing theories. Copernicus, Darwin, Einstein, all started with evidence that forced humanity to reconstruct its understanding of reality from the ground up. The James Webb discoveries might represent the beginning of a similar revolution, one that will transform not just cosmology, but our entire conception of existence itself. We stand at the threshold of a new cosmic story, one that might reveal the universe to be eternal, infinite, and far more mysterious than we ever imagined. The telescope that was built to confirm our origin story might instead be opening the first chapter of an entirely new book of cosmic understanding. The greatest adventures in discovery aren't behind us. They're waiting to be written in the light of ancient galaxies that refuse to follow our rules, in the spin of impossible stars, and in the organization of a universe that seems to have known exactly what it was doing from the very beginning. The story of how the universe came to be isn't ending. It's just beginning to be told.